Let's jump right into this explainer. I want you to picture a perfectly normal scene. Let's say it's a standard Tuesday afternoon. You're sitting at your desk, or maybe you're cruising down the highway, just going about your day. Then, suddenly, without absolutely any warning at all, the entire world jerks violently to the side. Objects launch sideways at nearly 1,000 miles per hour. Buildings are literally erased. The oceans turn into these massive supersonic tidal waves. Now, I know it sounds like some wildly exaggerated Hollywood apocalypse movie, but actually, it's just pure unadulterated physics. This is exactly what would happen if the Earth simply locked its brakes. See, right now, as you sit watching this, you are riding on a massive planetary carousel. We're traveling at roughly 1,000 miles per hour at the equator. And the crucial thing to remember here is that if the planet suddenly stops, you don't. Your body, your house, the asphalt under your tires, even the entire atmosphere, it would all just keep flying forward at the speed of a jet fighter. It is literally the ultimate kinetic whiplash. The atmosphere would sweep across the continents like a global broom, triggering these supersonic winds that would scrub the Earth's crust completely bare. But okay, let's play along and say you somehow survive that initial shockwave. What happens next is honestly far more terrifying. The actual geometry of our entire world would rewrite itself. Because our Earth spins, centrifugal force causes the planet to bulge outward at the equator. But if that spin suddenly stops, gravity pulls the planet back into a perfect sphere. The oceans would instantly migrate away from the equator and rush toward the poles. You'd end up with two massive, completely isolated polar oceans separated by a single, towering megacontinent wrapping entirely around the equator. Oh, and your daily routine? Yeah, a single day would now last an entire year. You'd endure 6 months of scorching, uninterrupted daylight, followed by 6 months of absolute freezing darkness. It really kind of makes you realize just how fragile our cosmic equilibrium actually is.
Section 1. Cosmic Apex Predators, the monsters in the dark.
So, our fragile little rock is held together by this perfectly tuned celestial clockwork. But if we zoom out to places where physics completely breaks down, we find monsters that logically shouldn't even exist. To really grasp their scale, just think about the volume of a single marble. We used to think of black holes as, just science fiction math props. But today, we are literally looking at the silhouettes of these monsters. A stellar mass black hole can cram the entire mass of our sun into a space roughly the size of a small American city. If you were to squeeze the entire Earth down until it became a black hole, it would be the size of a single marble. Just imagine that, a literal marble sitting in the palm of your hand, but containing the gravity of an entire planet. Crazy, right? And that incomprehensible density creates what we call the event horizon. Now, this isn't a physical surface you can actually touch. It's a boundary where the escape velocity of space exceeds the speed of light itself. It's basically a terrifying cosmic door. Once you cross that threshold, the universe literally closes its doors behind you. There is absolutely no coming back. But what actually happens if you cross that door? Well, it depends entirely on who's watching. The time dilation effects are genuinely eerie. If you were falling into a black hole, an outside observer wouldn't actually see you fall in. To them, you'd appear to slow down as you approach the event horizon, eventually looking frozen in time forever, just slowly fading into a dark red smear. But to you, falling in, you'd watch the entire future history of the universe flash before your eyes in a matter of seconds. And then, the physics takes over. You would be stretched into a single atom-wide thread by the immense gravity. It's a horrific process that scientists actually literally call spaghettification. But here is the massive plot twist. These absolute apex predators aren't just destructive forces tearing the universe apart. They are the architects of the cosmos. They actually hold the universe together. Every major galaxy we know of, including our very own Milky Way, revolves around a supermassive black hole. They maintain the entire structure of our universe by simultaneously tearing physics apart at their core.
Moving on to Section 2, the Mars reality check, leaving the cradle.
So, if the Earth's spin is that vulnerable, and black holes are just wandering the dark, what is humanity's insurance policy? Right now, that policy is being written by NASA and its partners through the Artemis missions, using the moon as a sort of cosmic sandbox to prepare for the colonization of Mars. But look, we need to shatter this sci-fi utopia myth right now. The internet loves to paint this rosy picture of glass domes and cybertrucks jumping over red dunes, but the reality is stark. On Earth, we breathe a lovely mix of nitrogen and oxygen. On Mars, it's 95% carbon dioxide. The average temperature plummets to a brutal -80 degrees Fahrenheit. And perhaps the most deadly part, radiation. Earth has a magnetic shield protecting us, Mars does not. You are constantly being baked by unshielded cosmic rays. Mars is definitely not a utopia. It is a toxic, freezing desert actively trying to kill us in multiple ways simultaneously. Living there, it'll be closer to living inside a nuclear submarine buried under toxic dirt. And if you think you can just step outside for a quick walk to stretch your legs, you really need to understand the Armstrong limit. Because the atmospheric pressure on Mars is so incredibly low, if you walked outside without a highly specialized pressurized suit, your bodily fluids would literally boil at room temperature. It is a completely hostile, totally unforgiving environment. Which naturally leads to the big question on everyone's mind. Why do it? Seriously, I want you to really consider this. Why expend trillions of dollars, countless resources, and risk human lives to colonize a freezing, toxic desert that literally wants to boil your blood?
The answer really comes down to two words: survival distribution. History has shown us time and time again that species that keep all their eggs in one basket eventually get wiped out when that basket drops. Whether the threat is a rogue asteroid, a supervolcano, or, even our own destructive technology, becoming a multi-planetary species isn't about setting up some luxury off-world retreat. It is our ultimate insurance policy. It's the ultimate stress test of human ingenuity to ensure we just don't go extinct.
Section 3, the blind geniuses, ancient space mathematicians.
Let's ground all this high-tech cosmic survival talk by rewinding the clock a bit. We tend to think we're so advanced right now because we have supercomputers, James Webb telescopes, and particle accelerators. We naturally assume deep cosmic knowledge requires deep tech. But centuries before NASA, well before the European Enlightenment, ancient scholars were mapping the exact same universe using nothing but shadows, geometry, and pure, unfiltered mathematics. Take 500 CE, for example. The ancient Indian mathematician Aryabhata dropped a bombshell treatise mapping the cosmos. This was over 1,000 years before Copernicus published his heliocentric theory, and way before Galileo famously faced the Inquisition in 1633 for even suggesting the Earth moved. Aryabhata was centuries ahead of the curve.
And his breakthroughs? Absolutely staggering. Aryabhata stated flatly that the Earth is a perfect sphere. He figured out that it rotates on its own axis. He deduced that the apparent rising and setting of the stars wasn't the sky moving, but an optical illusion caused by our own planet's spin. He even realized that the moon doesn't shine on its own, but rather reflects sunlight. And he achieved all of this conceptual genius without a single lens or telescope. And the precision of their math? It is just mind-blowing. Using only mathematical principles, Aryabhata calculated the Earth's circumference to be roughly 24,835 miles. Today, using advanced satellites and laser telemetry, we measure it at 24,901 miles. I really want to let that sink in for a second. That is an error margin of just 0.2%, and it was achieved 1,500 years ago. And it doesn't stop there. Here is another staggering calculation. The Surya Siddhanta, an ancient astronomical text from the exact same era, calculated the length of the sidereal solar year to be exactly 365.256 days. When you compare that ancient calculation to the measurements of our modern atomic clocks, it is accurate down to a matter of minutes. So how is that even possible? Well, they treated the sky as a giant living mathematical canvas. They mapped planetary orbits by inventing the very trigonometry, the sine and cosine functions, that we use in advanced aerospace engineering today. The human mind has always been our greatest space telescope. We didn't discover the cosmos when we built metal rockets. We discovered it when we first looked up and realized the universe speaks entirely in the language of mathematics.
Section 4, the cosmic perspective.
Whether we are looking backward at the staggering naked-eye genius of ancient astronomers, or looking forward to the modern engineers building pressurized habitats on the Martian horizon, it all comes together to remind us of our delicate existence. We are a really young species, sitting on a tiny rock spinning at 1,000 miles an hour through a beautiful, chaotic vacuum. A sudden stop ruins everything, a nearby black hole swallows everything, and yet, against all odds, here we are, measuring the stars and planning our next planetary home. I want to leave you with this final, awe-inspiring thought. We are a piece of the universe that has finally opened its eyes to look back at itself. So as you go about your normal Tuesday, I have to ask you, what will we choose to look at next? Thanks for joining me on this explainer. Keep looking up and stay curious.